Howdy, we are FloBotics and we're presenting our project showcase presentation. I'm Joseph Kim, project manager.
I'm Luke Benninger, hardware engineer.
I'm Yuzhe Pei, software engineer.
I'm Gyuyoung Jeong, integration engineer.
Our technical advisor is David Malloway and our project sponsor is Dr. Goulart. This is our project overview and we'll be starting with the background information first. So what is currently being done? Most greenhouses employ 3 different methods for indoor ventilation. The first method utilizes controlled airflow using mechanical means such as fans. The second method incorporates active systems such as an evaporative cooling ball, while the third common method involves a combination of both passive and active cooling. For healthy crops, most indoor agricultural facilities aim for an overall airflow of 1.34 meters per second, while also employing vents on the walls and roofs to help exhaust warm air. What is not being done? On the flip side, there are some important characteristics that are not taken into account. Currently, there are no practical methods for measuring airflow in specific increments for indoor agricultural applications. This means that there are no commercially available autonomous robots that are able to alleviate the tedious work that would be required to take measurements in accurate time and location intervals. In addition to the lack of a commercially available robot, there are no available graphical user interface that would provide the user with the airflow data within the entire greenhouse. Last but not least, without the ability to measure airflow at certain intervals within the indoor space, tracking any potential harmful contaminants that travel through the air is difficult as they are not visible to the naked eye. Project justification. With all the characteristics that are not being done in current indoor agriculture application, FloBotics' Ventus aims to deliver a product that will be capable of taking airflow measurements at specific time and location intervals. In addition to airflow data, Ventus will be capable of measuring temperature, barometric pressure, and humidity data. And by utilizing open source and commercially available hardware, Ventus will potentially be affordable to reach a wide range of customers from amateur growers to professional commercial grade indoor facilities. Existing problem. So a common inaccuracy for indoor agricultural systems stems from the lack of airflow measurements in proximity to ventilation systems. This may lead to desirable initial readings, but ultimately provides incorrect overall ventilation conditions. In addition, most agricultural control systems lack a mean of visualizing distributed airflow within a confined space. Another major existing problem is the presence of airborne substances such as mold spores, carbon monoxide, ammonia, and cold traps, all which have the ability to prevent crops from growing properly. The chosen solution by FloBotics is to develop a robot by 2022 that would be capable of autonomous operation throughout a greenhouse while collecting airflow, humidity, temperature, and barometric pressure data. Once the data collection has been completed, the data will be transmitted through wireless communication. The same transmitted information will be retrievable in 2 methods. The first method is to digitally aggregate data to be displayed on a private web server via GUI, while the second method involves local retrieval by USB for more granular details.
Here is our functional requirement. The FloBotics robot travels around perimeter of the indoor space. It is built on the open source Scuttle platform as seen in the figure. Also, the FloBotics robot utilizes RP LiDAR A1 over the USB. In the sensor board, airflow sensor will be primary focus. It includes other components to measure environment conditions such as temperature, humidity, and pressure. The main computational unit is Raspberry Pi 4, and it provides interface for sensor boards and wireless communication. The functional requirements of the data transmission is to utilize Sigfox development board and communicate on Sigfox low power wide area network. It will have end-to-end encryption for security and the local data storage option over the USB. The graphical user interface GUI has function for the visualization of the data. Here is our conceptual block diagram. The Scuttle travels around indoor greenhouse with LiDAR passing system, and all the sensors boards will be installed on the Scuttle. The data collection will be occurred at the certain points during the pass. The collected data will be transmitted in certain time period, and it'll be encrypted and sent to Sigfox server. Then it will be visualized via GUI. All the data can be stored into storage device such as the USB. This is our performance specification for the LiDAR passing plan. Scuttle starts in a corner facing the first direction of the travel. The LiDAR is mounted on the side of the robot facing the wall. We will single out 3 values from the LiDAR. X is the distance from the wall, YB as the distance behind the robot, and YF the distance in front of the wall. The total distance of the wall is considered the value. The steps are as follows. The robot will record the required value, then the robot will drive the straightforward while utilizing encoder and Y value as a While using the Y values to travel in 1 feet increments, the robot will stop to take sensor readings and record the position related starting point. Once the robot reached the corner, this means that YF value will be equal to X. Then the robot will rotate 90-degree counterclockwise. This process will be repeated 3 times for the full parameters of the.
Here is the performance specification for our 6-Fox module. With 6-Fox module, which is a low data rate and low power and small package with the PyCom expansion board, we can also send in the GPS coordinate. As you can see inside the figure, the blue colors is which means the coverage, the 6-Fox network coverage. And here is our testing code for our 6-Fox module. And as you can see, this page showing the 6-Fox website backend, and it's actually receiving data from our 6-Fox module. And here's the part for, here's the performance specification for our software, which is about the GUI. It's a graphical user interface. It's created by Python. It's available access through website with login features. And it also can display clear visualization of airflow data and also allow user to analyze the sensing data. Here is our overall software flowchart. We break our overall software to 4 different stages. The first one is basic stage, which control the Scala robot basic movement. The second one should be data collection and navigation stage. The third one should be user backend. The last one should be encryption.
This is the functional block diagram for a Metis robot system. On the left are the inputs. This includes the LiDAR, the airflow sensor system, and the environmental sensor. The PAV305D airflow sensors are connected through a multiplexer. This is done to mitigate the issue of multiple I2C devices with the same address. Up top is the power system, which is based off the scuttled 12-volt battery pack. The 5-volt regulator is for the Raspberry Pi, which handles most computation. On the right are our outputs. This includes a motor driver for 2 12-volt motors, 2 wheel encoders, and the low-pi 6-Fox module. The intended voltages and communication protocols are listed for every device. Next is our hardware design. Since accurate 3-dimensional airflow measurements are very important to our project, we focused on creating a capable sensor array. This array of 6 sensors will be mounted on a 3D printed sphere like the diagram shown. Since each PAV305D sensor is directional, they can be configured in opposing directions for a final directional calculation on the Raspberry Pi. Inside the sphere will be the multiplexer board and a controllable RGB LED for robot and sensing indication. The sphere will be 3D printed from translucent filament for this capability. The individual airflow sensors come in an SMD form factor for mounting to a PCB. To use these sensors on our sphere, we will create 6 identical PCBs using the schematic shown. These PCBs will utilize quick connectors on the back of the board for easy and reliable connection to our multiplexer board.
So the impact of the project. Beyond Texas A&M University, FloBotics Ventus will provide potential customers with improved growing experience by providing a constant stream of indoor airflow data through an online service. Along with a better growing experience, there are potentials for reducing energy costs by allowing Ventus users to strategically implement active ventilation in locations that have the greatest impact, rather than attempting to provide uniform airflow for an entire indoor space. To help keep crops healthy, the use of Ventus will help users to potentially identify and track harmful airborne contaminants by their airflow vector path. And the last impact is the documentation of LiDAR and sensor board integration with the Scuttle platform, which will serve as reference material for future Scuttle applications. Thank you very much for your attention, and we await your feedback.